Hello astronomers! This week you're going to be learning about planet formation and how star systems and planet systems form not only our own solar system but solar systems throughout the galaxy. And so what I wanted to do today is take a little bit of time to talk about the features of the solar system that we need to explain in order to come up with a reasonable theory of how planets form. The forces that are acting in our solar system, the dominant force is gravity, right? So if we have whatever our formation mechanism is, it has to include this idea of gravity acting on massive objects. So what we're looking at here is the inner solar system, and I'm using a program called Universe Simulator that you can get for Mac or PC if you're interested in doing this type of exploration. And I'm going to hit play here, and we're going to watch the inner solar system go around here. And the first thing we notice about the planets in our solar system is that for the most part they orbit in the same direction. They all orbit counterclockwise, and we define the motion of the planets with the northern hemisphere of the planets pointing, in this case, out of the page, and then everything is orbiting counterclockwise. So you see Mercury is going around, Venus is going around, Earth, Mars, and then if we go out a little bit further, you'll see Jupiter and Saturn and Uranus and Neptune. And so in fact, even the Sun is on a little orbit because it's orbiting a common center of mass, like we learned in the gravity section. The other thing we'll notice about the planets is that the interior planets are going faster, according to Kepler's laws, than the planets that are further outside. We do have some planets, most of the planets are on circular orbits, but we have small debris, like here's an asteroid coming in, here's another asteroid coming in, that are orbiting the Sun counterclockwise, but they're not on circular orbits, they're on elliptical orbits that are plunging in to the inner solar system, and some of those even cross Earth's orbit. So there is this general tendency of things to be orbiting in the same direction. The other thing we'll notice, and I'm just going to pan down a little bit here, is that the solar system by and large is a disk, right? Now it's not entirely a disk. There's some vertical distribution, especially for the small objects, like the asteroids and things like that. But for the most part, the planets orbit in a disk. So these, whatever the formation mechanism is, has to be able to form a disk of material as things form. The other thing you'll notice, and I'm going to pause this really quickly, and I just want to zoom in on the Earth real quick. The other thing you'll notice is that the planets themselves, for the most part, spin counterclockwise. So this is the Earth spinning counterclockwise, and I can zoom in on Mars. Let me pause this real quick. I can zoom in on Mars and see the same thing, that it tends to be spinning counterclockwise. But it's not true for everything. For example, if I look in on Venus, which is about the same size as the Earth, we're going to see that it is orbiting in the other direction, or it's rotating in the other direction. So Venus is actually rotating clockwise compared to the rest of the planets. So the second thing we'll notice about our solar system is that most of the planets rotate counterclockwise, but not all of them. In fact, there's another planet called Uranus, which if I zoom in on that one, you'll see that it is tilted almost 90 degrees on its side. So if you watch, it's hard to see it rotate because there aren't very many surface features, but the rotation basically tilted on its side like this. Is it rotating clockwise or counterclockwise? Well, it depends on which way you flip it up or down. And in fact, with Venus, you could even argue that Venus isn't rotating clockwise, that it's just flipped over on its top. And it's rotating counterclockwise, but the North Pole is pointing down. So we need to be able to explain that most of the planets are orbiting in a similar direction. They're rotating in a similar direction, but not necessarily all of them. And there are even some small objects that orbit in a clockwise direction around the Sun. Those are called retrograde planets. Okay, so just to recap, we have a couple of pieces of data that we need to examine. The first one is that the planets orbit the sun in nearly all the same direction. The other one is that they tend to be in mostly circular orbits, although there are some small objects that are on elliptical, very elliptical orbits. They tend to orbit in the same, or rotate in the same direction, although not all of them. And the solar system appears to be mostly a disk, although there are some notable exceptions, like even Pluto and Charon and other small objects are not exactly in a disk. So whatever solar system formation mechanism we have has to explain those features. Now again, the first thing that happens in a solar system is that gravity starts to pull everything together, right? Now when that happens, the random motions add up to have some very gentle rotation in some direction. There's going to be some net rotation, and as this thing collapses, it's going to start to spin faster, and it's going to tend to spin in the same direction. So the idea that things are spinning in the same direction kind of naturally comes around from the collapse due to gravity and the conservation of angular momentum. The disk is a little bit easier to understand because if you think about material coming in and hitting each other as it's collapsing, right? If it's coming in at an angle, or if it's coming in straight up and down, it's going to tend to hit and bounce off, right? But if things are spinning, if you've got two objects coming in, if I can do this right, if you've got two objects coming in like this, and they are rotating in the same direction, but they have some z motion, then when they hit, they're going to go off together, right? Just like two cars hitting and going off together. So as things collapse and everything begins to interact with each other, we tend to see the thing flattening into a disk, because as things that are coming from the top and the bottom hit each other, they tend to go off in the direction that everything is rotating. So those are the two things, the two formation mechanisms that we think gives us the general tendency of everything to orbit in the same direction and the general tendency of things to form a disk. Some other things we need to be able to explain that you'll learn about in this section is the difference between the interior planets, which tend, let's zoom in on the interior planets here. The interior planets, which tend to be mostly rocky. So Venus, Mercury, Earth, and Mars tend to be mostly solid rocky materials. As we go further out, we get more of the gas giants, Jupiter, Saturn, Uranus, and Neptune, which are gaseous planets that don't really have a rocky surface to speak of. And then collected all around there is a bunch of debris. So what causes what distinguishes these different types of planets is something we have to think about. And we had a pretty good story for that when we talked about our solar system, because the massive giant gaseous planets were far out, the rocky planets were close in. It turns out that rock condenses at a higher temperature than some of the gassy stuff, so having a solid rock close to a hot star makes sense. Turns out from our study of exoplanets that we're finding gas giants that are near to the central star, and it turns out they need to form far away and then migrate in, so you'll be learning all about that when we talk about exoplanets. But I hope this little demonstration just gives you an idea of how we use the observations of what we see in our own solar system and other solar systems, and the knowledge that we have about the physical forces to formulate a story of how things came to be. All right, so that's what you're going to be learning about this week, and I will look forward to seeing you soon.